The ocean covers 71% of our planet's surface. It holds 97% of Earth's water. And yet, we've explored less than 5% of it. Right now, beneath the waves, there are mountains taller than Everest, canyons deeper than the Grand Canyon, and creatures stranger than anything in science fiction. Tonight, we're diving into the deep, where sunlight never reaches and pressure could crush a submarine like a tin can. The zone, where light dies. There's a place in the ocean where sunlight gives up. It's not a specific location, it's a depth. Around 200 meters down, depending on water clarity, the last photons of sunlight fade into absolute darkness. Scientists call this the twilight zone, or the mesopelagic zone. Below this lies the midnight zone, where no natural light has penetrated for millions of years. Imagine descending into this darkness. At the surface, the ocean is blue and bright, waves sparkling in sunlight. You begin to sink. At 10 meters, the reds disappear from the spectrum. Everything looks blue-green. At 30 meters, the orange is gone. By 100 meters, yellow fades. The world becomes increasingly monochrome, shades of blue-green growing dimmer with every meter you descend. At 200 meters, you're in perpetual twilight. Some light remains, but barely. A dim glow that makes shapes visible, but reveals no color. Your eyes strain to see. The water around you is no longer empty. Shadows move through the gloom. Creatures you can't quite make out drift past, appearing and disappearing like ghosts. Then, at about 1,000 meters, even this faint light is gone. You're in complete darkness. Not the darkness of a moonless night on land. That darkness has stars, has ambient light reflected from somewhere. This is absolute darkness, the absence of any light whatsoever. You could hold your hand inches from your face and see nothing. But the darkness isn't empty, it's full of life, more life than scientists imagined until recently. The deep ocean, once thought to be a barren desert, is actually teeming with creatures. They've evolved to survive in conditions that would kill surface-dwelling animals instantly. The pressure at 1,000 meters is about 100 times atmospheric pressure at sea level. At the deepest parts of the ocean, nearly 11,000 meters down in the Mariana Trench, the pressure exceeds 1,000 times surface pressure. That's like having a large elephant standing on every square inch of your body. Yet creatures live there. Fish with bodies adapted to the pressure, with proteins and cell membranes that function in these extreme conditions. Many are small, energy efficient, moving slowly to conserve precious calories in an environment where food is scarce, and many create their own light. Bioluminescence, the ability to produce light through chemical reactions, is incredibly common in deep-sea creatures. Estimates suggest that 90% of animals in the EEA, deep ocean, can produce light. They use it to hunt, to communicate, to confuse predators, to attract mates. In the absolute darkness of the deep ocean, these creatures create their own stars. Flashes of blue-green light appear and vanish. Some fish have light organs under their eyes like headlights, illuminating prey. Others have lures dangling in front of their mouths, glowing to attract smaller fish. Some create sudden bursts of light to startle predators. Others release clouds of glowing chemicals like smoke screens made of light. The twilight zone, between 200 and 1,000 meters, hosts one of the largest animal migrations on Earth. Every night, countless small fish, squid, and crustaceans rise from the depths to feed in surface waters. Every dawn, they descend again, fleeing the light and the predators that hunt by sight. This vertical migration involves more biomass than any other animal migration on the planet. More than the great wildebeest migrations, more than bird migrations. It happens every day, in every ocean, largely invisible to human eyes. Scientists are only beginning to understand the scale of life in the deep ocean. For centuries, we assumed the deep sea was nearly lifeless. Too dark, too cold, too much pressure. But every expedition discovers new species, new behaviors, new ecosystems. The deep ocean isn't empty, it's alien. When submersibles descend into the abyss, their lights reveal creatures that seem impossible. Jellyfish the size of cars, their bodies transparent except for glowing organs. Fish with teeth so large they can't close their mouths. Squid with eyes the size of dinner plates. Worms that grow to lengths of several meters, their bodies segmented and bristling with appendages. Most of these creatures have never been seen alive at the surface. They can't survive the pressure change. When brought up in nets, they often die or their bodies deform. So our understanding comes from brief glimpses through submersible windows, from cameras lowered into the deep, from sonar mapping that reveals movement but not detail. The deep ocean is Earth's last frontier. We have better maps of the moon's surface than of our own ocean floor. We've sent humans to the moon, but only a handful of people have descended to the deepest parts of our ocean. The deep sea remains largely unexplored, unmapped, unknown, and it's vast. The ocean's average depth is about 4,000 meters. There are underwater mountain ranges that span thousands of kilometers. Trenches that plunge to depths where the pressure could compress a human body to the size of a marble. Plains of sediment stretching for hundreds of miles, slowly accumulating the remains of dead organisms drifting down from above like eternal snow. In this darkness, in this pressure, in this cold, life persists. It adapts. It thrives in its own strange way. The deep ocean teaches us that life is more resilient, more versatile, more creative than we give it credit for. It shows us that Earth still holds mysteries, that we don't know everything about our own planet, that there are frontiers we've barely begun to explore. As you drift toward sleep, imagine that darkness, absolute, complete, unbroken except for the occasional flash of bioluminescence. Imagine the silence, broken only by the subtle sounds of creatures moving through water. Imagine the cold, the pressure, the alien beauty of a world that exists just miles below the ocean's sunlit surface, yet might as well be on another planet. The sounds beneath the waves. In 1997, researchers listening to underwater microphones in the Pacific Ocean recorded a sound. It was extremely loud, loud enough to be detected on sensors over 5,000 kilometers apart. The sound rose in frequency over about 1 minute, starting at a low rumble and ascending to a higher pitch. Researchers called it the bloop. No known animal could produce a sound that loud. No geological event matched its characteristics. The bloop was analyzed, debated, and theorized about for years. Some suggested it was a massive unknown creature, something far larger than a blue whale, the largest animal ever known to exist. Others proposed geological explanations, ice movements, volcanic activity, tectonic shifts. Eventually, scientists concluded that the bloop was most likely caused by an ice quake, the sound of a massive iceberg fracturing and breaking apart. But before that explanation emerged, the bloop represented one of the ocean's great mysteries, an unexplained sound from the deep, raising the possibility that something unknown was down there. And here's the thing. The ocean is full of unexplained sounds. The ocean isn't silent. That's a common misconception. It's actually quite noisy, filled with sounds that travel much farther and faster underwater than they do in air. Whale songs carry across entire ocean basins. Snapping shrimp create sounds so loud they can interfere with sonar. Fish grunt, croak, and drum. Ice cracks and groans. Underwater volcanoes rumble. Earthquakes produce low-frequency sounds that circle the globe multiple times. Humans have been listening to the ocean systematically since the Cold War, when networks of underwater microphones called hydrophones were installed to track submarines. After the Cold War ended, some of these systems were made available for scientific research. Suddenly, researchers could listen to the ocean on a global scale. They heard things they couldn't explain. Strange sounds appearing and disappearing. Patterns that seemed biological but didn't match any known species. Low-frequency rumbles from unknown sources. High-frequency clicks that appeared in sequences suggesting communication, but in frequencies and patterns unlike anything documented. One sound, called upsweep, has been detected continuously since it was first recorded in 1991. It's a long series of narrowband upsweeping sounds that occur several times per minute. Scientists believe it's geological in origin, possibly related to volcanic activity, but its exact source has never been pinpointed. Another sound, Julia, was recorded in 1999. It lasted for about 15 seconds and was loud enough to be heard on multiple sensors. Its source was never identified, though researchers speculate it might have been an iceberg running aground. Slow down is a sound that was recorded multiple times in the late 1990s. As its name suggests, the sound's frequency slowly decreased over about 7 minutes. Again, the source was never conclusively identified, though ice movement is the leading theory. These name sounds are just the famous ones. There are countless other unexplained sounds in the ocean archives, brief anomalies, strange patterns, noises that don't fit known categories. But let's talk about the sounds we do understand, because they're just as fascinating. Whale songs are among the most complex, non-human vocalizations known. Humpback whales sing elaborate songs that can last for hours. All the males in a population sing variations of the same song, which slowly evolves over time. They're literally creating and sharing a cultural tradition. The songs can be heard over hundreds of kilometers. Researchers have recorded the same song spreading across the Pacific, changing and adapting as it moves from one whale population to another. Blue whales produce some of the loudest sounds made by any animal, reaching up to 188 decibels. For comparison, a jet engine at takeoff produces about 140 decibels. These low-frequency calls can travel across entire ocean basins, potentially allowing whales thousands of miles apart to communicate. Sperm whales produce clicks that are the loudest sounds made by any animal, up to 230 decibels. They use these clicks for echolocation, hunting squid in the deep ocean where light doesn't penetrate. The clicks are so powerful, they can potentially stun or even kill their prey. But whales also produce sounds we don't fully understand. Some whale species make complex sequences of calls that resemble language in their structure. They have syntax, rules for combining sounds. They have dialects. Different populations use variations of calls. Young whales learn vocalizations from their mothers and podmates, just as human children learn language. Are they talking? We don't know. We can't translate whale calls the way we might eventually decipher an unknown human language, because we don't share a common frame of reference. We can identify that certain calls are used in certain contexts, feeding, socializing, mating, navigating, but the actual content, if there is content beyond simple signaling, remains mysterious. Then, there's the loneliest sound in the ocean. In 1989, researchers detected a whale calling at 52 hertz, much higher than the typical 15 to 25 hertz of blue and fin whales. This whale has been tracked migrating annually along the Pacific coast for decades. It's alone, calling in a frequency that other whales might not recognize or respond to. Researchers call it the 52 hertz whale, though some call it the loneliest whale in the world, singing songs no one else can understand. The ocean also transmits sounds from the surface world. Ship engines create constant low-frequency noise that fills the oceans, potentially interfering with whale communication. Sonar from military and commercial vessels can be harmful or even deadly to marine mammals. The ocean's soundscape has been fundamentally altered by human activity. But listen deeper, away from shipping lanes and coastal areas, and you can still hear the ocean as it was for millions of years. The clicks and whistles of dolphins, the grunts of fish, the crackle of snapping shrimp, the groans of ice, the rumble of underwater landslides, the subtle sounds of currents moving past underwater mountains, and beneath it all perhaps sounds we haven't yet learned to detect or interpret. The ocean is vast, and we're still learning to listen. The giant that vanished. For centuries, sailors told stories of massive creatures rising from the depths, tentacles thick as ship masts, wrapping around vessels and dragging them under, eyes the size of dinner plates, glowing in dark water, bodies longer than whales, the kraken, they called it, the monster of the deep. Scientists dismissed these as superstitions, exaggerations, the hallucinations of sailors too long at sea. There was no evidence of such creatures. The largest known squid were modest in size, a few feet long at most. But the sailors were right. Giant squid exist. They can grow to over 40 feet in length, with eyes up to 10 inches in diameter, the largest eyes in the animal kingdom. Their tentacles are lined with hundreds of sucker discs, each rimmed with sharp teeth. They hunt in the deep ocean, using bioluminescence and excellent vision to spot prey in near total darkness. For over a century, scientists had indirect evidence of giant squid. Dead specimens occasionally washed ashore or were found in the stomachs of sperm whales, which hunt them. But no living giant squid had ever been observed in its natural habitat. They seemed to exist only as corpses and fragments. Then, in 2004, Japanese researchers managed to photograph a living giant squid in the wild for the first time. They used a camera attached to a baited line, lowered nearly a kilometer into the ocean. The squid attacked the bait and became entangled. It struggled for over 4 hours before finally tearing free, leaving behind a tentacle. The photographs were revolutionary. They showed a powerful predator, aggressive and fast-moving, nothing like the sluggish scavenger some scientists had imagined. The squid's skin changed colors as it struggled, flashing reds and whites. Its arms reached out in coordinated movements. It was clearly hunting, not just happening upon the bait by chance. In 2012, the same research team captured the first video footage of a giant squid in its natural habitat, about 1 kilometer deep in the Pacific Ocean. The footage showed a juvenile, about 3 meters long, swimming gracefully through dark water. Its arms trailed behind it, its large eyes reflected the submersible's lights, its skin shimmered with changing colors. That footage lasted just a few minutes. The squid swam away into darkness and disappeared. But those minutes revealed more about giant squid behavior than centuries of studying dead specimens. We now know they're not rare. They're just good at avoiding detection. They live in deep water across the world's oceans. They grow quickly, reaching large sizes within a few years. They hunt fish and smaller squid. They're hunted by sperm whales, which dive to great depths specifically to catch them. The scars on many sperm whales show evidence of dramatic battles, circular marks from squid suckers covering the whales' heads and bodies. But giant squid aren't even the largest squid species. That title belongs to the colossal squid, which lives in the deep waters around Antarctica. Colossal squid have heavier, more robust bodies than giant squid, with hooks on their tentacles in addition to suckers. The largest known specimen was about 14 meters long and weighed nearly 500 kilograms. Only a few colossal squid specimens have ever been found, all dead. No one has filmed a living colossal squid in the wild. They remain among the ocean's great mysteries. We know they exist. We know roughly where they live. But we've never observed their behavior in nature. Think about that. These are animals the size of school buses living in our oceans right now, and we've never seen them alive in their natural habitat. They could be common or rare. We don't know. They might live alone or in groups. We don't know. Their entire life cycle remains mysterious. And if giant squid and colossal squid could remain unknown or poorly understood until the 21st century, what else is down there? What other large creatures might exist in the deep ocean, living their lives beyond human observation? There are hints. Unidentified marks on whales suggesting encounters with something large. Sonar readings detecting massive objects moving through deep water. Occasional reports from deep-sea fishermen of creatures they can't identify. Most turn out to be known species seen from unusual angles or under unusual conditions. But occasionally, there's something that doesn't quite fit existing categories. The ocean is vast enough and deep enough to hide creatures we haven't discovered yet. Not sea monsters from medieval legends. Those are clearly mythical. But large, rare animals adapted to depths we rarely explore. That's not just possible, it's likely. Every year, scientists describe dozens of new marine species. Most are small. New types of shrimp, worms, jellies. But occasionally, something larger emerges. In 2006, a new species of whale was identified. The Amura's whale, up to 12 meters long, previously confused with other whale species. In 2012, researchers confirmed that what had been considered one species of orca was actually 3 distinct species, large animals living in our oceans, and we're still learning to tell them apart. The ocean teaches humility. It reminds us that Earth still has mysteries, that discovery isn't finished, that the next expedition into the deep might reveal something entirely unexpected. The giant squid that sailors described for centuries turned out to be real. What else might be real? Waiting to be found. The Lost City. On the floor of the Atlantic Ocean, about 800 meters below the surface, there's a field of ghostly white towers rising from the seafloor. They're made of carbonate and silicate minerals, sculpted by hydrothermal processes into structures that look like Gothic architecture. Spires and columns and walls, some reaching over 60 meters tall. Scientists call it the Lost City Hydrothermal Field. But the Lost City isn't lifeless ruins. It's very much alive. Hydrothermal vents are places where seawater seeps into the ocean floor, gets heated by underlying geological activity, and rises back up carrying dissolved minerals. When the hot water meets cold ocean water, the minerals precipitate out, forming chimney-like structures. Over time, these chimneys grow taller and more elaborate. Most hydrothermal vents are black smokers. They expel water heated to over 400 degrees Celsius, rich in sulfides that form black plumes. These vents support bizarre ecosystems based not on sunlight but on chemosynthesis. Bacteria that derive energy from chemicals in the hot water, forming the base of a food chain completely independent from the surface world. But the Lost City is different. Its vents are relatively cool, only 40 to 90 degrees Celsius. They emit white plumes rich in carbonates, and they're powered not by volcanic activity, but by a chemical reaction between seawater and rocks in the Earth's mantle, a process called serpentinization. This matters because serpentinization might have been crucial for the origin of life. The reaction produces hydrogen and methane, simple molecules that can fuel basic metabolisms. The warm, alkaline vents provide chemicals, energy gradients, and mineral surfaces that could facilitate the chemical reactions necessary for early life. Some scientists believe that life on Earth might have originated at places like the Lost City, not at the surface, exposed to UV radiation and meteor impacts, but in the sheltered environment of deep-sea vents, where chemical energy was abundant and conditions were relatively stable. The Lost City has been active for at least 30,000 years, and possibly over 120,000 years. Its towers are old, built gradually by mineral precipitation, layer upon layer. Some are riddled with channels and cavities, creating complex internal structures. These cavities are inhabited by microbes, bacteria, and archaea that metabolize the chemicals in the vent fluids. Unlike black smoker vents, which support large animals like tube worms and crabs, the Lost City's ecosystem is primarily microbial. The organisms there are tiny, living in biofilms coating the mineral surfaces, metabolizing hydrogen and methane, existing at the boundary between geology and biology. The discovery of the lost city in 2000 changed our understanding of where and how life can exist. If life can thrive in these conditions on Earth, then similar environments on other worlds might also support life. Jupiter's moon. Europa has a subsurface ocean beneath its ice shell. Saturn's moon Enceladus has geysers of water erupting from a subsurface ocean. If these oceans have hydrothermal activity, and evidence suggests they might, then they could have environments similar to the lost city. Life on these moons wouldn't need sunlight. It wouldn't need a thick atmosphere or a temperate surface. It would need only water, rock, and heat, conditions that might be common throughout the solar system and beyond. The lost city also teaches us about Earth's interior. The serpentinization reaction that powers the vents occurs when seawater reacts with mantle rocks. This means that seawater is penetrating deep into the Earth's crust, possibly circulating through cracks and fractures to depths of several kilometers. Water from the surface mixes with rocks from the mantle, altering both in the process. This has implications for the water cycle, for mineral formation, for the chemical balance between Earth's surface and interior. The ocean and the solid Earth aren't separate systems. They interact constantly, exchanging materials and energy. Standing in a submersible at the lost city, if you could stand there, you would see the white towers rising around you like monuments in a sunken cathedral. The water would be warm, much warmer than the surrounding deep ocean. Shimmering fluids would rise from the vents, white plumes ascending toward the distant surface. The mineral structures would glow in your lights, their surfaces covered in microbial biofilms, teeming with invisible life. And you would be looking at something ancient, not just in years, but in significance. You would be looking at the kind of environment where life might have begun, where chemistry became biology, where the first cells might have formed and divided and evolved. You would be looking at a process that might be common throughout the universe, wherever water and rock and heat come together. The lost city is still being studied. Research expeditions visit periodically, taking samples, measuring temperatures and chemical compositions, documenting changes over time. Each visit reveals new details about how the system functions, how the minerals form, how the microbes survive. But the lost city is fragile. Its location is known, which means it could be damaged by careless research or, in the future, by mining operations seeking rare minerals. Protecting it has become a priority for ocean conservation efforts. There's something profound about a place so remote and so ancient still being vulnerable to human impact. The lost city has existed for tens of thousands of years, unchanged and undiscovered. Now that we've found it, we have the power to destroy it. Whether we choose to protect it instead says something about our relationship with the ocean, with discovery, with the unknown. The sharks that lived forever. In the cold waters of the Arctic and North Atlantic, there swims a creature that might be the oldest vertebrate on Earth. The Greenland shark grows slowly, living in deep, frigid water, moving through darkness like a ghost. Scientists estimate that some individuals alive today could be over 400 years old. 400 years. That means there are sharks swimming in the Arctic that were born during the reign of James the Murderers of England, before the Pilgrims reached America, before Galileo observed Jupiter's moons. Sharks that have lived through the entire span of modern history, through every war, every revolution, every scientific discovery. Sharks older than any tree currently living, older than any other animal we've found. How do we know this? The age of fish is usually determined by counting growth rings in hard tissues like bones or scales. But sharks don't have bones. Their skeletons are made of cartilage. Greenland sharks don't even have scales in the traditional sense, so scientists had to develop a different method. They used radiocarbon dating on the eye lenses. Fish eye lenses grow throughout life, adding layers like tree rings. The center of the lens forms before birth and remains metabolically inert. It doesn't change chemically after formation. By dating the carbon in the center of the lens, scientists can determine when the shark was born. The results were stunning. One female shark was estimated to be 392 years old, give or take 120 years. Even at the lower end of that range, she would be over 270 years old. Other large individuals were estimated to be 335 years old, 272 years old. Greenland sharks grow about 1 centimeter per year. They don't reach sexual maturity until they're about 150 years old. Think about that. A century and a half before they can reproduce. Their slow growth, slow metabolism, and cold environment all contribute to extreme longevity. But longevity comes with vulnerability. Greenland sharks are occasionally caught as bycatch in fisheries. They're killed for their liver oil. Their populations are poorly understood and likely declining. An animal that lives for centuries can seem abundant, but if they're being killed faster than they can reproduce, population collapse can happen before anyone notices. And Greenland sharks aren't the only animals with remarkable lifespans. The ocean is home to creatures that challenge our understanding of aging and death. Ocean quahogs are clams that can live for over 500 years. One individual, nicknamed Ming, was determined to be 507 years old when it was collected in 2006. It was born during the Ming Dynasty in China, hence the nickname. These clams sit on the seafloor, filtering plankton from the water, growing incrementally, adding a ring to their shell each year. Glass sponges in the deep ocean might live for over 10,000 years. Dating them is difficult because they grow so slowly and irregularly, but analysis of their skeletons suggests some individuals have been alive since the end of the last ice age. And then there are the immortal jellyfish. Turritopsis dohrnii, a small jellyfish found in oceans worldwide, can potentially live forever. When injured or stressed, it can revert to its polyp stage and then develop into an adult again, essentially resetting its life cycle. Whether any individual jellyfish actually achieves immortality in the wild is unknown. Most are probably eaten or killed by environmental factors, but the theoretical possibility exists. These ancient animals live mostly in cold, deep water where metabolism is slow, predation is low, and conditions are stable. Aging, in some ways, is a consequence of damage accumulating faster than it can be repaired. In these cold, stable environments, damage accumulates very slowly, but there's more to it than just slow living. These animals must have cellular mechanisms that prevent the usual aging processes. Their DNA must be protected from damage. Their cells must avoid accumulating mutations. Their proteins must remain functional across centuries. Understanding how these animals achieve such longevity could have implications for human aging. If we understood the genetic and cellular mechanisms that allow a shark to live for 400 years, could we apply that knowledge to extend human health span? Could we prevent or slow age-related diseases? Research is ongoing, but these animals are difficult to study. They live in remote, hostile environments. They're rare and long-lived, making population studies challenging. Collecting samples without harming the animals requires specialized equipment and expertise. When you encounter a Greenland shark, if you ever do, you're meeting an elder of the ocean, an animal that has lived through centuries of change, that carries in its body a history longer than any human lifetime. It moves slowly through dark water, its clouded eyes nearly blind, navigating by smell and sensing electrical fields. Many Greenland sharks have parasites attached to their eyes, small crustaceans called copepods that damage the cornea, causing blindness. The sharks don't seem bothered. They hunt primarily by smell, feeding on fish, seals, and carrion that sinks from above. They're scavengers as much as predators, eating whatever the ocean provides. There's something humbling about an animal that old. It reminds us that our perspective on time is limited. We think in terms of decades. These sharks exist in terms of centuries. The ocean operates on timescales that dwarf human experience. The slow accumulation of sediment, the gradual movement of currents, the patient growth of coral reefs, the centuries-long lives of individual animals. The sea that glows. On certain nights, in certain places, the ocean glows. Step into the water and your feet create swirls of blue-green light. Move your hand through the water and sparks trail from your fingers. Boats leave glowing wakes. Fish become visible as luminous silhouettes. The entire sea seems to be full of stars. This is bioluminescence, light produced by living organisms. In the ocean, it's incredibly common. As we mentioned earlier, up to 90% of deep-sea animals can produce light. But bioluminescence isn't limited to the deep. It occurs in surface waters, too, creating displays that have amazed sailors and coastal people for millennia. The most common cause of bioluminescent bays and beaches is dinoflagellates, single-celled organisms that flash with light when disturbed. The light is produced by a chemical reaction. A protein called luciferin reacts with oxygen, catalyzed by an enzyme called luciferase. The reaction releases energy as light rather than heat. A remarkably efficient process. But why? Why do these tiny organisms produce light when disturbed? The leading theory is that it's a defense mechanism. When a small predator, like a tiny fish or crustacean, tries to eat dinoflagellates, they flash with light. This sudden illumination might startle the predator, causing it to spit out the dinoflagellate. Or the flash might make the predator visible to larger predators, creating a burglar alarm effect. The dinoflagellate essentially calls for help by illuminating its attacker. Whatever the reason, the effect is spectacular. In places like Mosquito Bay in Puerto Rico, or Luminous Lagoon in Jamaica, or certain beaches in the Maldives, the concentrations of bioluminescent dinoflagellates are so high that any movement in the water creates visible light. Swimming in bioluminescent water is surreal. Every stroke illuminates the water around you. Droplets falling from your raised hand glow like liquid stars. Fish darting away create streaks of light. You're literally glowing, covered in a constellation of single-celled organisms announcing their disturbance at your presence. But dinoflagellates aren't the only bioluminescent organisms in the ocean. Jellyfish, comb jellies, various fish species, squid, octopuses, worms, crustaceans, and even some sharks can produce light. Each has evolved bioluminescence independently, using it for different purposes. Some deep-sea fish have light organs called photophores under their eyes, shining like headlights to illuminate prey. Others have glowing lures to attract prey toward their mouths. The anglerfish is the most famous example, with its glowing bulb dangling in front of its face. Some squid and fish use bioluminescence for counter-illumination. They produce light on their undersides, matching the faint light filtering down from above. This makes them invisible to predators looking up from below, their silhouette erased by their own light. Some creatures use bioluminescence to communicate. Fireflies aren't the only animals that signal with light. Some deep-sea squid flash complex patterns that might convey information to other squid. Some fish use light displays during courtship, and some use it defensively, in creative ways. Certain squid, when threatened, release clouds of glowing mucus that confuse predators. Some shrimp create sudden bursts of light to startle attackers. Some jellyfish detach glowing parts of their bodies as decoys. The variety of bioluminescent systems in the ocean suggests it evolved independently dozens of times. It's such a useful adaptation in dark water that evolution discovers it repeatedly, using different chemicals, different proteins, different mechanisms to achieve the same result: light without heat. Humans have been fascinated by bioluminescence throughout history. Ancient sailors witnessed glowing wakes behind ships and told stories of sea spirits. Coastal people saw glowing waves and attributed them to magic. Even now, swimming in bioluminescent water feels magical, like something from a fairy tale. Scientists have found practical uses for bioluminescence. The luciferin luciferase reaction has become a standard tool in research, used as a marker to track genetic expression, detect the presence of ATP, measure bacterial contamination. The 2008 Nobel Prize in Chemistry was awarded for the discovery and development of green fluorescent protein, originally from a bioluminescent jellyfish. But beyond practical applications, bioluminescence is simply beautiful. It's nature creating art, light in darkness, life announcing its presence in the void. It's evolution producing something that seems unnecessary. Surely survival doesn't require beauty. And yet beauty emerges anyway. On a dark beach, when conditions are right, you can wade into glowing water and feel connected to something ancient and universal. The same chemistry that lights up dinoflagellates around your feet occurs in deep-sea creatures miles below. The same evolutionary pressures that created bioluminescence in ancient oceans still operate today. The ocean has been glowing for hundreds of millions of years, and it will continue glowing long after we're gone. The current that moves the world. Imagine a river in the ocean, not a river of fresh water flowing through salt water. Those exist too. But a river of moving water within the ocean itself, driven by temperature and salinity differences rather than by gravity and topography. The ocean has currents, and these currents connect every part of the global ocean into one system. Water from the Arctic flows to the Antarctic. Water from the surface descends to the depths and returns centuries later. The entire ocean circulates, slowly but constantly, driven by differences in temperature and salt content. Scientists call it the thermohaline circulation, or more poetically, the global ocean conveyor belt. It's one of the most important systems on Earth, regulating climate, distributing nutrients, affecting weather patterns across the globe. Here's how it works. In the North Atlantic, near Greenland and Labrador, surface water is cold and relatively salty. Cold, salty water is dense. It sinks, descending thousands of meters to the ocean floor. This downwelling creates a vacuum that pulls in more surface water from the south. The sinking water flows south along the ocean bottom, eventually reaching the Southern Ocean around Antarctica. In the Southern Ocean, the deep water from the North Atlantic meets water that has descended around Antarctica. The combined deep water mass flows eastward, driven by the Antarctic Circumpolar Current, the strongest current in the ocean, uninterrupted by land, circling Antarctica at depths and speeds that move 100 times more water than all the world's rivers combined. From the Southern Ocean, the deep water flows northward into the Indian and Pacific Oceans. Slowly, over centuries, this deep water gradually warms and rises. Eventually, after traveling through all the ocean basins, it returns to the surface in the North Pacific. From there, surface currents carry it westward, through the Indonesian archipelago, across the Indian Ocean, around the southern tip of Africa, and back northward in the Atlantic, completing a journey that takes about 1,000 years. 1,000 years for a drop of water to complete the circuit. Water that sank near Greenland during the Middle Ages is only now rising in the Pacific. Water sinking today won't return to the surface until the year 3000. This circulation system does several critical things. First, it distributes heat. The Gulf Stream, part of the surface portion of this system, carries warm water from the tropics northward, along the coast of North America and across to Europe. This warmth moderates Europe's climate. London, at 51 degrees north latitude, has a milder climate than Calgary, Canada, at the same latitude because of the Gulf Stream's influence. Second, the circulation distributes nutrients. When water sinks in the North Atlantic, it carries dissolved oxygen to the deep ocean. When water rises in the Pacific and Indian Oceans, it brings nutrients from the deep back to the surface, fueling the plankton blooms that support entire marine ecosystems. Third, the circulation stores carbon dioxide. The ocean absorbs CO2 from the atmosphere. Some of this CO2 is incorporated into marine organisms and sinks as those organisms die. But much of it simply dissolves in seawater. When water sinks in the North Atlantic, It carries dissolved CO2 to the deep ocean, effectively removing it from the atmosphere-ocean surface system for centuries. The ocean has absorbed about a quarter of all the CO2 humans have released into the atmosphere since the Industrial Revolution. This has slowed climate change, but at a cost. The absorbed CO2 makes the ocean more acidic, affecting calcifying organisms like corals and shellfish. But here's the concern. The thermohaline circulation can change. It has changed in the past, sometimes dramatically and suddenly. Ice core records from Greenland show that during the last ice age, temperatures in the North Atlantic region changed by as much as 10 degrees Celsius within a decade. Change is far too rapid to be caused by orbital variations or gradual climate shifts. Something was causing abrupt reorganizations of the climate system. The leading explanation involves the thermohaline circulation. When large amounts of fresh water enter the North Atlantic, from melting ice sheets for example, the surface water becomes less salty. Less salty water is less dense. It doesn't sink as readily. If the sinking stops or slows significantly, the entire circulation system can weaken or even shut down. When this happens, heat distribution changes. Europe, deprived of the Gulf Stream's warmth, can cool dramatically. Ocean ecosystems, deprived of the usual nutrient distribution, can collapse. Weather patterns worldwide can shift. The effects cascade through the Earth system. Evidence suggests the circulation has slowed by about 15% since the mid-20th century, the weakest it's been in over 1,000 years. This is likely due to increased fresh water input from melting Greenland ice and increased precipitation in the North Atlantic. Whether this will continue, whether it represents a temporary fluctuation or a longer-term trend, and what the consequences might be are active areas of research. The thermohaline circulation is one of the Earth's great engines, operating invisibly, moving vast quantities of water and heat and nutrients. We didn't even know it existed until the late 20th century. We're still learning how it works, how stable it is, how it interacts with other parts of the climate system. It's humbling to realize that something so fundamental to Earth's climate was unknown for most of human history. The ocean kept this secret, circulating its waters, regulating the climate, supporting life, all without any human awareness or intervention. And it reminds us that the ocean isn't just a passive body of water, it's an active system, constantly moving, mixing, transporting, transforming. The ocean you see from the beach, with its waves and tides, is just the surface. Beneath lies a three-dimensional world of currents, flowing at different depths, in different directions, driven by forces operating on time scales from hours to millennia. The deepest place on Earth. The Mariana Trench in the western Pacific Ocean contains the deepest point in Earth's oceans. Challenger Deep, named after the HMS Challenger that first measured the trench's depth in 1875, reaches approximately 10,794 meters below sea level. That's almost 11 kilometers straight down. To put this in perspective, if you placed Mount Everest at the bottom of the Mariana Trench, its peak would still be covered by over 2 kilometers of water. The pressure at the bottom is crushing, about 1 to 100 times atmospheric pressure at sea level. That's equivalent to about 8 tons per square inch, or having roughly 50 jumbo jets stacked on top of a person. For decades, scientists believed nothing could survive at such depths. The pressure seemed incompatible with life. Any organism would be crushed, its proteins denatured, its cell membranes ruptured. But life, as always, found a way. In 1960, Jacques Picard and Don Walsh descended to Challenger Deep in the Bathyscaphe Trieste. They were the first humans to reach the deepest point on Earth. In the brief time they spent at the bottom, they observed a flatfish swimming past their viewport. Life existed even here, in the most extreme environment on Earth. Since then, unmanned submersibles and landers have explored the trench multiple times. They've found numerous species living at these depths: amphipods, fish, sea cucumbers, microbial communities. These organisms have evolved remarkable adaptations to survive the pressure. Their cells contain special molecules that stabilize proteins under extreme pressure. Their membranes have different lipid compositions that remain fluid despite the pressure. They have no air-filled spaces that could be compressed. Some have eliminated certain proteins and structures that become non-functional at high pressure, streamlining their biology to function in this extreme environment. The fish found at these depths, snailfish in the family Leporidae, are small and translucent, with gelatinous bodies that handle pressure better than more rigid structures. They lack scales and swim bladders. Their bones are poorly mineralized, more cartilaginous, allowing more flexibility. They're perfectly adapted to a world of crushing pressures and near-freezing temperatures and complete darkness. But beyond the living organisms, the Mariana Trench holds another surprise: pollution. In 2019, researchers found plastic bags and candy wrappers at the bottom of Challenger Deep. Microplastics have been found in amphipods collected from the trench. Human pollution has reached even the most remote, deepest part of the ocean. This discovery is both scientifically interesting and deeply troubling. It shows that the ocean is more interconnected than we thought. Materials from the surface can reach the deepest trenches. But it also shows that nowhere in the ocean is beyond human impact. We've touched every part, contaminated every depth, from the surface to the deepest point on Earth. The Mariana Trench also provides insights into Earth's geology. It's a subduction zone, where one tectonic plate slides beneath another. The Pacific Plate is being forced beneath the smaller Mariana Plate, creating the deep trench. As the Pacific Plate descends, water trapped in its rocks is released, triggering volcanic activity that creates the Mariana Islands. This process, plates colliding, one descending beneath the other, is fundamental to plate tectonics. It recycles old ocean crust back into the Earth's mantle. It creates volcanic arcs. It drives earthquakes. The trenches are where old ocean floor goes to die, dragged down into the mantle to be remelted and recycled. Deep in the trench, pressures are so high that water behaves differently. It's denser than normal water. Its structure is altered by the pressure. Some scientists speculate that exotic forms of ice might exist at the bottom of the deepest trenches. Ice formed not by cold, but by pressure, remaining solid despite temperatures above freezing. Only 4 descents by humans have been made to Challenger Deep. The Trieste in 1960, James Cameron in the Deep Sea Challenger in 2012, and Victor Vescovo, who made multiple dives in 2019. That's fewer people than have walked on the moon. The deep ocean remains more inaccessible to humans than space. When you descend to these depths, the journey takes hours. The submersible sinks through the water column, passing through ecological zones as distinct as different planets. The sunlit surface zone, teeming with life. The twilight zone, where light fades and bioluminescence begins. The midnight zone, absolutely dark except for the occasional flash of a bioluminescent creature. The abyssal zone, the vast plains of the deep ocean floor. And finally, the Hadal zone, the trenches named after Hades, the Greek underworld. At the bottom, you're in a world of soft sediment, near freezing water, and pressure that would instantly kill any surface organism. Yet amphipods scuttle across the sediment. Fish swim slowly through the water. Microbes metabolize organic matter that drifts down from above. Life persists, adapted to conditions that seem impossible. The view is limited. Your lights illuminate only a small area. Beyond lies darkness, extending in all directions. You're sitting at the bottom of over 10 kilometers of water, with the weight of the entire ocean above you. It's the closest you can come to visiting another planet while staying on Earth. The singing ice. Antarctica is surrounded by ice shelves extending from the continent, icebergs calved from glaciers, sea ice forming on the ocean surface. This ice interacts with the ocean in complex ways, creating sounds that scientists have only recently begun to understand. Ice shelves, thick platforms of ice floating on the ocean while still attached to the land, are constantly moving. They flex with tides. They respond to ocean swells. They crack and groan under their own weight. And they sing. In 2017, researchers placed seismometers on the Ross Ice Shelf, one of the largest ice shelves in Antarctica. The instruments were meant to detect seismic activity, the rumbles and quakes that indicate ice movement. What they recorded was unexpected. The ice shelf was vibrating constantly, producing a nearly continuous tone. The pitch varied with weather conditions. When wind rearranged the snow on the ice shelf surface, the vibrations changed frequency. The ice shelf was essentially a giant musical instrument played by the wind. These vibrations are too low frequency for human ears to hear. They're in the infrasonic range. But when sped up, they sound like a haunting hum, rising and falling, creating an eerie song that plays continuously. Why does this matter? Because changes in the ice shelf structure, thinning, cracking, melting, would change its vibrational properties. By monitoring these vibrations, scientists can detect changes in the ice shelf that might not be visible from satellites or surface observations. The ice shelf song can tell us when it's weakening. But the ice doesn't just sing. It also speaks in more dramatic ways. When icebergs calve from glaciers, they create events called ice quakes. These are similar to earthquakes, but they're caused by ice breaking rather than tectonic plates moving. Large calving events release enormous amounts of energy, equivalent to earthquakes of magnitude 5 or higher. The sound travels through the ocean for hundreds or thousands of kilometers. Remember the bloop, the mysterious sound we discussed earlier? It was likely an ice quake, a massive iceberg fracturing and breaking apart. Ice, despite being solid, is under constant stress. It flows like a very slow liquid creeping toward the ocean under its own weight. Eventually, stress fractures develop. When they finally give way, the release is explosive. Icebergs themselves continue making noise after they break free. As they melt, they crack and pop. Trapped air bubbles, compressed for thousands of years, are released suddenly. The sounds are sometimes called ice sizzle, a continuous crackling and popping as ancient air escapes. And then there are the sounds of ice forming. In the coldest parts of Antarctica, where sea ice forms rapidly, the ice cracks as it expands, creating sounds like gunshots echoing across the frozen ocean. Pressure ridges form where ice sheets collide, grinding and crushing with sounds like distant thunder. Scientists studying Antarctic ice use hydrophones, underwater microphones, to listen to these sounds. The acoustic environment beneath Antarctic ice is rich and complex. The songs of seals calling beneath the ice, the clicks of shrimp, the low rumbles of ice movement, the groans of ice shelves flexing with tides, the sharp cracks of ice breaking. This soundscape is changing. As the climate warms, ice shelves are thinning. Their songs are changing frequency. Some ice shelves have collapsed entirely. The Larsen B ice shelf, which had been stable for 10,000 years, disintegrated in just 6 weeks in 2002. When it went, its song stopped. The sounds of ice aren't just scientifically interesting, they're also eerily beautiful. Recordings of ice singing, of icebergs cracking, of pressure ridges forming, create a kind of natural music. Some composers have incorporated these sounds into musical works, creating pieces that blend human composition with the voice of the ice itself. But beneath the beauty is a warning. The ice is speaking to us, telling us about its condition. The changes in its song reflect changes in its structure. As the climate continues to warm, the ice's voice is changing. Some sounds are becoming rarer. Some are becoming more common. The orchestra of Antarctic ice is being rearranged. In the Arctic, similar processes occur. The Arctic Ocean's sea ice cover has been declining for decades. Thinner, smaller in extent, lasting for shorter periods each year. The sounds are changing there too. Where there was once solid ice throughout winter, there's now open water. Where there were once quiet, ice-covered seas, there's now the sound of waves and wind. The ice remembers. Ice cores drilled from Antarctic ice sheets contain air bubbles from ancient atmospheres, trapped when the snow fell and was compressed into ice. By analyzing these bubbles, scientists can reconstruct past climates going back 800,000 years. The ice holds a record of Earth's history, written in layers of snow and trapped air. And the ice is speaking now, singing its slow song, telling us about its past and warning us about its future. Whether we listen, whether we understand, whether we act on what the ice is telling us, that remains to be seen. The forest beneath the waves. Off the coast of California, in the cold, nutrient-rich waters of the Pacific, there are forests. Not forests of trees, but forests of kelp. Giant algae that can grow over 150 feet tall, creating underwater canopies as dense and complex as any rainforest on land. Kelp forests are among the most productive ecosystems on Earth. The kelp itself grows incredibly fast, up to 2 feet per day in ideal conditions. This rapid growth is fueled by sunlight and the cold water's abundant nutrients, brought up from the deep by ocean currents. The kelp provides structure. Thousands of organisms live in kelp forests, fish hiding among the fronds, invertebrates clinging to the stalks, sea urchins grazing on the eazut, holdfasts that anchor kelp to the rocky bottom. Sea otters hunt for urchins and abalone. Harbor seals rest among the kelp. Gray whales pass through during migration. Sharks patrol the edges. Swimming through a kelp forest is like moving through a three-dimensional maze. Sunlight filters down through the canopy, creating shafts of light that dance as the kelp sways with the current. The fronds are thick and slippery, reaching toward the surface. Schools of fish dart between the stalks. The water is cold, typically around 50 to 60 degrees Fahrenheit, but full of life. But kelp forests are fragile. They require cold water, rocky substrates, and a delicate balance of grazers. When that balance is disrupted, entire kelp forests can disappear within months. The main threat comes from sea urchins. Sea urchins eat kelp, grazing on the holdfasts and stalks. Normally, their populations are controlled by predators, primarily sea otters, but also some fish species. But when predator populations decline, urchin populations explode. The urchins form what's called an urchin barren, a large area of rocky bottom covered with urchins, stripped clean of kelp. In the mid-1800s, sea otters were hunted nearly to extinction for their fur. With sea otters gone, urchin populations exploded along much of the Pacific coast. Kelp forests disappeared, replaced by urchin barrens. The entire ecosystem collapsed, not just the kelp, but all the species that depended on it. Conservation efforts brought sea otters back in some areas. Where otters returned, they ate the urchins, and the kelp forests regrew. Within a few years, a barren rocky bottom can transform back into a lush kelp forest. This is what scientists call a trophic cascade, the presence or absence of a top predator cascading through the entire ecosystem, affecting every level down to the primary producers. But kelp forests face other threats too. Ocean warming can make water too warm for kelp, which prefers cold temperatures. Marine heat waves, periods of unusually warm water, can kill kelp over large areas. Pollution can reduce water clarity, limiting the light available for kelp photosynthesis. Disease can strike kelp populations, causing mass die-offs. In recent years, large kelp forests off the coast of California and Australia have experienced significant die-offs. The causes are complex, a combination of warming water, marine heat waves, and changes in urchin predator populations. Once a kelp forest is lost, recovery isn't guaranteed. Urchin barrens can persist for decades if conditions don't change. Kelp forests aren't unique to California. They exist around the world in temperate and subpolar coastal waters. Along the coasts of Chile, South Africa, southern Australia, New Zealand, and in colder northern waters around Alaska, Canada, Norway, and Japan. Each has its own species of kelp and its own associated community of organisms. The kelp itself is remarkable. It's not a plant, it's a brown. Algae, more closely related to diatoms than to land plants. It doesn't have roots, stems, or leaves in the traditional sense. What looks like roots are holdfasts, structures that anchor the kelp to rocks but don't absorb nutrients. What looks like a stem is called a stipe. What looks like leaves are blades, and many kelp species have gas-filled bladders that help the blades float near the surface where light is abundant. Kelp has been used by humans for thousands of years. Coastal peoples harvested it for food. It's edible and nutritious, rich in minerals and vitamins. They used it as fertilizer for crops. In more recent times, kelp has been harvested industrially for alginates, compounds used in everything from ice cream to toothpaste to pharmaceutical capsules. But kelp's most important role is ecological. Kelp forests are nurseries for many fish species. They protect coastlines from storm waves. They absorb carbon dioxide from seawater. They provide habitat for countless organisms. Losing them has cascading effects throughout coastal ecosystems. There's something magical about diving in a kelp forest. The play of light through swaying fronds, the sense of being in a wild, living place, the fish that dart past, the seals that peer at you curiously, the rhythmic sway of the kelp with the ocean's pulse. It feels primordial, like glimpsing what the ocean has been for millions of years. But it's also fragile. These forests can vanish, replaced by barren rock and urchins. Whether they persist depends on factors both natural and human: ocean temperatures, predator populations, water quality, climate change. The fate of kelp forests, like so much in the ocean, is uncertain. The blue holes scattered across tropical seas, particularly in the Caribbean and the Pacific. There are perfectly circular openings in the shallow ocean floor. From above, they appear as dark blue circles against the lighter turquoise of surrounding shallow water. These are blue holes, flooded cave systems that offer windows into the Earth's past. The most famous is the Great Blue Hole off the coast of Belize. It's almost perfectly circular, 318 meters across and 124 meters deep. From the air, it's stunning. A dark sapphire circle in the turquoise Caribbean, rimmed by lighter, shallow water. Blue holes form in limestone. During ice ages, when sea levels were lower, rain would slowly dissolve the limestone, creating cave systems. Stalactites and stalagmites grew in these caves, like in any cave system. Then, when the ice melted and sea levels rose, the caves flooded. If the roof of a cave collapsed, it created a vertical shaft open to the surface, a blue hole. The Great Blue Hole was originally a cave system that formed during the last ice age when sea level was 120 meters lower than today. The cave collapsed, creating the sinkhole. As sea level rose, the hole flooded. Now the surface is at modern sea level, but the hole extends down into what was once dry cave. Diving into a blue hole is like diving into history. At the surface, there's normal Caribbean marine life, tropical fish, corals around the rim. As you descend, the walls become steeper, the light dims. Around 40 meters down in the Great Blue Hole, you reach a ledge where massive stalactites jut out from the walls, angled in the direction they grew when this was a dry cave thousands of years ago. These stalactites prove that the cave was above water when they formed. Stalactites only form in air, from water dripping through cave roofs and depositing minerals. Their presence underwater is evidence of lower sea levels in the past. Their angle shows how the cave roof collapsed. They're tilted because the rock they're attached to tilted when it fell. Below the stalactites, the hole continues deeper into darkness. The water is still, stratified, layers of different salinity and temperature that don't mix much. Below a certain depth, oxygen levels drop dramatically. Few organisms live in the deeper parts. It's a largely static environment, cut off from the ocean's circulation. But blue holes aren't just in the open ocean. Some exist on land, in flooded cave systems that connect to the sea through underground passages. These are even more mysterious and dangerous. Divers have explored some of these systems, mapping underwater cave passages that extend for kilometers, rising and falling, branching and reconnecting, creating labyrinths beneath the surface. Cave diving is one of the most dangerous forms of diving. The passages are often narrow and silty. Disturbed sediment can reduce visibility to 0 in seconds. There's no direct route to the surface. You must retrace your path through the cave system. Running out of air isn't just dangerous, it's fatal. Many experienced divers have died in blue holes and underwater caves. But the exploration continues because these cave systems hold secrets. Paleontologists have found fossils in blue holes, bones of extinct animals that fell into the caves when they were above water. In blue holes in the Bahamas, researchers have found fossils of crocodiles, tortoises, and birds that lived in the Caribbean thousands of years ago. Some blue holes also preserve records of ancient climate. Sediment layers in blue holes can show hurricane history going back thousands of years. When major hurricanes pass over a blue hole, they can deposit a distinct layer of coarse sediment. By examining these layers, scientists can reconstruct hurricane frequency and intensity over millennia, long before humans were recording such events. And some blue holes preserve evidence of ancient human activity. In blue holes in Mexico's Yucatan Peninsula, divers have found human skeletons and artifacts dating to over 12,000 years ago, when these caves were dry and were being used by Paleo-Indian people. Some of these are among the oldest human remains found in the Americas. The underwater environment has preserved these remains remarkably well. Bones that would have decayed or been scattered if left on land have remained intact in the still water of submerged caves. The caves are accidental time capsules, preserving whatever fell or was placed in them before the sea level rose. There are blue holes still being discovered. Remote sensing, including satellite imagery and airborne surveys, continues to identify previously unknown blue holes in shallow tropical seas. Some are being explored for the first time, revealing new cave systems, new geological features, new evidence of the past. Each blue hole is unique. Different depths, different cave structures, different connections to the surrounding ocean. But all of them are windows into the past, showing us what the landscape was like when sea levels were lower, preserving evidence of ancient environments and ancient life. Floating at the edge of a blue hole, looking down into the dark blue depths, you're looking at the past and the present simultaneously. The shallow water around you is the present. Modern sea level, current ecosystems. The deep hole below is the past. A cave system from the last ice age, now flooded, holding secrets from a time when humans were just beginning to populate the Americas, and mammoths still walk the earth. The silent ending. We've traveled through the ocean tonight, from the surface to the deepest trenches, from tropical seas to polar ice, from bright coral reefs to dark vents smoking on the seafloor. We've met creatures ancient and bizarre, discovered places beautiful and strange, encountered mysteries that persist despite centuries of study. The ocean is vast. It covers most of our planet. It contains most of our planet's living space. When you account for depth, the ocean represents over 99% of Earth's biosphere. Yet we've explored less than 5% of it. Less than 25% of the ocean floor has been mapped in any detail. Most of the ocean remains unknown. And this unknown isn't empty. It's not a void waiting to be filled. It's full of life we haven't documented, species we haven't named, ecosystems we haven't studied, processes we haven't understood. Every deep-sea expedition discovers new species. Every survey of coral reefs finds unexpected diversity. Every monitoring program reveals changes we didn't anticipate. The ocean keeps secrets not because it's trying to hide them, but because it's simply too large, too deep, too remote for us to have explored thoroughly. And perhaps that's okay. Perhaps some mysteries should remain unsolved. Perhaps some places should stay wild and unknown. But the ocean is changing. We've touched every part of it now, even the deepest trenches. Our plastics have reached the bottom of the Mariana Trench. Our carbon dioxide is acidifying the water. Our fishing nets are scouring the seafloor. Our noise is drowning out whale songs. Our shipping routes fragment marine habitats. Our pollution is creating dead zones where nothing can survive. The ocean that has existed for billions of years, that predates humans by unimaginable spans of time, that has weathered countless natural changes, is now being altered by a single species in the span of decades. We're conducting an experiment on the ocean, changing its chemistry, its temperature, its biology, without knowing what the results will be. Some changes are already visible. Coral reefs bleaching and dying, fish populations collapsing, dead zones expanding, ice melting, sea levels rising, ocean heat content increasing. Each year brings new records: warmest ocean temperatures, highest ocean acidity, lowest Arctic sea ice extent. But the ocean is resilient too. Marine protected areas are allowing some ecosystems to recover. Sea otter populations are rebounding in some regions, allowing kelp forests to regrow. Whales, protected from hunting, are slowly increasing in number. Coral restoration projects are showing that reefs can recover with help. The ocean wants to thrive. It just needs space to do so, and there's still so much beauty. Bioluminescent waves glowing in the night. Coral reefs teeming with colorful life. Whales breaching in sunlit water. Dolphins riding bow waves. Sea turtles gliding through blue water. Kelp forests swaying with the current. The simple pleasure of floating in warm water. The ocean holding you, rocking gently with its eternal rhythm. The ocean is where life began. The first cells formed in ancient seas, billions of years ago. Life moved onto land, but it never left the ocean. Most species still live there. And in some ways, we never fully left either. Our blood has a salt concentration similar to seawater. Our bodies are mostly water. Our earliest embryonic development goes through stages that look like fish. We carry the ocean within us, a reminder of where we came from. When you listen to the ocean, the sound of waves on a beach, the rush and pull of surf, the vast silence of deep water, you're hearing something ancient. These sounds have been part of Earth for as long as there's been liquid water and an atmosphere. They predated the first life, and they'll continue long after all current life is gone. The ocean's voice is eternal. As you drift toward sleep now, let your mind drift too. Imagine floating in dark water, weightless and free. Imagine descending through zones of light into darkness, surrounded by creatures that glow with their own light. Imagine ancient sharks swimming through deep water, living their centuries-long lives in cold and darkness. Imagine the slow circulation of ocean currents connecting all seas into one vast system. Imagine the ocean breathing, inhaling oxygen at the surface, exhaling it in the deep, breathing on a timescale of centuries. Imagine the waves, endless and rhythmic, rolling across thousands of miles of open water, carrying energy from distant storms. Imagine the deep sea vents, creating their own chemical worlds, supporting life in absolute darkness. The ocean keeps its mysteries. It holds them in its depths, in its darkness, in places human eyes haven't seen and may never see. And that's beautiful. Not everything needs to be known. Not every secret needs to be revealed. Some things can simply exist, mysterious and wild, untouched and unknowable. The water is dark. The pressure is immense. The cold is absolute. And still life persists, adapted to conditions we can barely imagine, thriving in ways we're only beginning to understand. If life can exist there in the harshest environment on Earth, then life is more tenacious than we thought, more creative, more resilient. And that gives hope. Whatever changes come, whatever challenges arise, life adapts. The ocean will persist. It may change. It is changing, but it will endure. It was here long before us, and it will be here long after we're gone. So rest now. Let the ocean's rhythm lull you to sleep. Let thoughts of deep water and ancient creatures and glowing waves fill your mind as consciousness fades. The ocean continues its eternal cycles, indifferent to whether we're awake or asleep, watching or absent. It simply exists, vast and mysterious, beautiful and terrible, familiar and alien. The ocean is home to mysteries we'll never solve. And maybe that's perfect. Maybe we need mysteries. Maybe we need places that remain unknown, that resist our attempts to map and measure and understand them completely. Maybe the ocean's greatest gift isn't what it reveals, but what it keeps hidden. Sleep well. The tide rises and falls. The currents flow. The deep-sea creatures go about their strange lives in darkness. The whales sing songs that travel across oceans. The coral polyps build their reefs, one calcium carbonate skeleton at a time. The ocean does what it has always done, what it will continue to do regardless of human presence or absence. And you are part of it. Water made conscious. Ancient ocean brought onto land, housed in skin, given thought and breath. You are the ocean, dreaming of itself. And now, as sleep comes, you return to those ancient waters in your mind, diving deep into dreams where boundaries dissolve and mysteries remain. Mysteries where questions don't need answers and the darkness is comfortable, welcoming, eternal. The ocean remembers everything, and now, so do you.